Hey guys, what's up? We're going to do some review for the dynamics test, which is tomorrow. So, we're going to do a couple of different kinds of problems here. We're going to talk about tension, pulleys, and inclined planes. I think we're good on elevators. We did that today in most of the classes, so I don't think we have any issues with elevators. If we do, let me know, and we can do an elevator problem. I think they're pretty straightforward. We can do one real quick. They're pretty simple. Why don't we go knock that out? Think about it. So we'll do an elevator problem real quick. All right. So elevators is at least 2, maybe 3 elevator questions on the test. I'll tell you that much. So you have an elevator, right? See, there's an elevator right here. My great drawing, and I got a person on the elevator. Here I am, or somebody. Okay, and they're standing on a scale. And remember from one of the quizzes we had that when you stand on a scale, the reading of the scale tells you the normal force, right? Because you're on a surface and it's pushing up on you. Okay. Now, when let's say the mass of this person is, 50 kilograms. Okay. Now, if you're on the scale and you're at rest or at constant speed, then the weight mg of the person is 500 newtons, and the normal force will push up with this same force, 500 newtons. Normal force when you're at rest or at constant speed. But when you hit the button to go to the top floor or whatever, you begin to accelerate. So if you have an acceleration, let's say, I don't know, 3 meters per second squared, now you're going to start accelerating. And from this point, we need to use Newton's second law, which we do on almost every problem. So make sure you know how to use this equation. And the m here is the mass of the person. That's our system. Acceleration is the person's acceleration. We know what that is already. It's 50 times 3. So that means my net force must equal 150, right? That's going to be 50 times 3. But the question is always, well, what forces make up the net force, right? There's more than one force kind of contained within this, symbol, so to speak, right? There's multiple forces in there that are adding up to 150. So what are they? Well, there's the normal force up, in, which is no longer just 500, right? Because we're not at rest any longer. So a question like this is generally going to ask you, what is the normal force? Or what does the scale read, right? So the normal force pushing up, and we're going to subtract the weight. That's the other force we have according to our free body diagram. And it's negative because, of course, it's pushing down. So we subtract this opposite direction. That's all going to have to equal 150 newtons. And then I'm just going to plug in what I know. I know mg is 500, right? That's because we're on Earth. So 500 newtons of n minus 500 equals 150. And then I'm going to just add 600 both sides to solve for n. Oh, sorry, 500. I don't know why I did 600. Brain fart. 500 both sides. Excuse me. And then these are going to cancel. So I have n equals 650 newtons. So the scale is going to read 650 newtons. Right? So that's how it's going to push up. So when you accelerate, that's arrow writing. Accelerate up. Right? If your velocity is up and you accelerate up, the scale is actually going to read higher than your actual weight. What happens when you velocity is up but you slow down? Let's see. Oops. Okay, if your velocity is up, velocity up, but acceleration down, that means your acceleration is negative, so you're slowing down now, right? So let's see, you're in an elevator, and you are on a scale, and it's a big scale. And say if you write a diagram, so we're going to have normal force up now, and weight down. Let's say same mass, so 500 newtons of weight. And now we'll say that the acceleration of the person is -2. All right, so they're beginning to slow down now, right? -2 because the acceleration is down towards the ground. Their velocity is up. Acceleration is opposite direction of velocity, so that means they're slowing down. And we're going to do the exact same thing we just did, net forces. So again, we want to find what does the scale read, right? What does the scale say? Net forces equals mass and acceleration. Acceleration is now -2. The mass was 50. That's going to equal my net force. So what are all the different forces being applied to the system, this person? We have the normal force up again, minus the weight again, like we did last time. The weight, of course, is 500 newtons. Now on this side of the equation, 50 times negative 2 is negative 100. So we're going to add 500 to both sides again, like I did last time. Except now we're going to see that our normal force is no longer bigger than our weight. It is now less than the weight. It's 400 newtons. All right, so what this is telling us is that when the acceleration is down, our normal force, the scale is going to read less than our own weight. Well, it has to, right? We're accelerating down. That means the net force must also be down, right? So that means that the normal force can't push up more than our own weight. It has to be less than the weight, so that when we add these two up, we get a vector pointing down. All right, so those are elevator problems. I think they're pretty straightforward once you kind of realize what's going on there. So just think about all the forces, use your Newton's second law equation, and you should be okay. All right, let's talk about the more challenging problems like inclined planes. So inclined planes are big tomorrow. At least 5 questions on inclined planes. Maybe it was 6. I don't remember. I think it's 5. But they're important. So let's just do a couple. We'll do 2 different problems here. We'll do one where we're trying to find a value of something. Let's try to find the acceleration. That's the common one. So we have acceleration, or we have an angle theta there. We have an object on an inclined plane. Let's say its mass m is 15 kilograms. Say theta is 30 degrees, and we have a coefficient of friction mu that is 0.3. And we want to find out what is the acceleration of this object on this inclined plane. No one's going to push it right now. Let's just keep it simple. So no one's pushing it. It's just going to slide down the ramp. So we draw a free body diagram first. It's always the first step. We got to see what our forces are. So here's our weight down, mg. We have the normal force up perpendicular to the surface. So we draw it up like this. That's N, normal force. We have the friction force, which now, if there was no friction, the block would obviously slide down the ramp, right, down to the left. But there is friction, so it's going to oppose that motion. Instead of being down the ramp, the friction opposes the motion, so it's going to push up. Force of friction. All right. So those are our three vectors. Now remember, we want to find components for any vector that does not align to our grid system, or however we're going to call it. Typically our system is vertical horizontal, but that's not going to work for us right now because this only works when we are on a flat surface. However, we are not on a flat surface, so we are going to erase that and say, okay, well, now our grid system needs to look like this, right? Parallel to the plane and perpendicular to the plane. What's the plane? I use that word a lot in class, and what I mean is the surface, right? The plane, like a two-dimensional flat, surface. So the plane is the plane of the ground we're on right here, right? This is the plane, the surface that we're on. Okay. So everything needs to be perpendicular or parallel to that. So this one is perpendicular, this direction, and then this direction is parallel. I didn't draw it very well, but you get the idea. Well, it looks like our normal force is perpendicular, and the friction force is parallel. But this guy here is not. He is straight down, and that doesn't really line up with our system, does it? So we need different components for that guy. So we're going to do different color here. Let's go, I like orange. So we're going to do components. So we're going to have one component going down the ramp this way. Oh, that's not down the ramp, is it? My bad. Down the ramp this way. Down the ramp. I always want to draw my arrows, the components for weight down the ramp first. And when I say down the ramp, I mean literally like you're going to go down the ramp, right? That way. And then after that, we're going to do our component into the ramp. And again, when I say into the ramp, I mean literally like you're going into the ramp like this. So it's going to be down like this way. So those are 2 components. Now we know the weight force is 150 newtons because 15 times 10 is 150. So now that I know that, I can get my calculator out. If I can find it. Found it. And we're just going to use our trigonometry to find out what those other components are. So we have, let's see here. We're going to do, remember this is theta. The reason why I want y'all to do it this way, down the ramp, into the ramp, is because you'll always know that this is theta. Okay? I know geometry can be weird sometimes and kind of looking at odd, but if we do it this way, you'll always know that that angle there is theta. That bottom part of the triangle will be theta every time. So that we know the angle is 30, right? We said it was 30 here. So we're going to use SOHCAHTOA. So we're going to do the opposite side. We'll use sine. So we'll do 150 sine of 30. That should get us the opposite side. So we 75. So I'm going to get the right color. This side is 75 newtons. And then we'll do 150 cosine of 30, and that is 130. We'll round it to the nearest whole number. 130 newtons. All right, so now I have my components. I know that the weight force, since the block can't physically move down, it can't go that way, right? The gravity force wants to pull the block down that way, but it can't pull the block down that way, right? Because the ramp's in the way. So instead, gravity compromises. It's like, okay, well, I'm gonna pull the block down the ramp this way with some force, and then I'll kind of push it into the ramp that way with some of the force. Okay, so that's why we have those two components. So now that I have those two components, I can literally, I'm going to erase the this component here because I don't want to get confused anymore. It's useless to me now. Once I help me find components, I don't care about it. It's gone. It doesn't exist to me anymore. I say thank you very much, and I say see you later. All right. Okay, one moment. I need to pause. All right, so as I was saying, now that we have these components, we can... right, so as I was saying, now that we have these components for the weight force, we can find out what these other two forces are. We're going to... we can now know the normal force must be equal to 130 newtons. If you look at the direction of this force and this force, notice that they're opposite directions, right? So they have to cancel out. The block is not going to float off the ramp or sink into the ramp, so it's not doing that, right? That'd be weird. So these two vectors must be equal and opposite, right? So 130 down into the ramp, 130 back out of the ramp. Now that we have that, we can use our formula for friction force, which is mu times n. We defined earlier the coefficient of friction to be 0.3, and now we know that the normal force is 130 newtons, so we just multiply those together, and we'll get our friction force. So friction force is, what is that? 130 times 0.3, 39 newtons. All right, so now we know friction force. Now that we know all the forces on our free body diagram, we can do a Newton's second law equation. All right, remember the goal. We're trying to find acceleration, right? That's our goal. So we know that Newton's second law says acceleration of an object is equal to the net forces divided by the mass of the system. Well, the normal force and this component here cancel out. So they're not relevant any longer, right? They helped us find the friction force, and that's kind of what their goal, their job was, and they're done. So now, which forces are left? We have the friction force up the ramp minus this component of weight down the ramp, so minus 75 newtons. All that divided by the mass of the system, which is the block, and now this box in this case is 15 kilograms. So, so we know what friction force is now. It's 39. So I'm going to go over here and finish. So we have 39 minus 75 divided by 15. So that's what is that? 39 minus 75 divided by 15. 2.4. Negative 2.4. Why negative? Well, it's going down the ramp, right? So we said down was negative, so there we go. All right. So that's one problem that you might see tomorrow. Almost certainly we'll see tomorrow. Let's do two more. I want to one more like inclined plane problem, and then we'll do a tension. That'll be a few more to do. So let's see how it goes. Feel free to skip around and see whatever you want. All right, let's try one more inclined plane problem. This time I want to do a flat surface, and I'm going to have an object on the surface. And instead of it being on an incline, I'm going to have the force applied be up at an angle. So flat ground this time, but we're, it's a ramp, or not a ramp, but an incline force. So I'm gonna draw this horizontal line here so I can see what the angle is. Call this theta. Let's say theta is 35 degrees. So the mass of the block M is, I don't know, how about 20 kilograms? And let's do a problem where you know what? Actually, let me erase this. I want to do a problem where we don't have any numbers, because you gotta learn how to not use numbers sometimes. So let's just derive an expression, your favorite. Let's derive an expression for acceleration. Derive an expression for acceleration. Okay, and we'll have the coefficient of friction is mu. But let's not put any numbers to anything. Let's just kind of fiddle with the, variables without any numbers. All right, so we still should draw a free-body diagram. That's still step one. So we have our weight of the box down. We have the applied force up this angle. We had the friction force going to push back this way, friction force, and normal force straight up. Right. Now, since there are no numbers, we can't, we're not going to know what the numbers are, but we still need to find components, right? That's still part of this process. So now we're on a flat surface. So the planes we want to use now are horizontal and vertical. That we don't want to tilt anything because we're on a flat ground. So there's still one force here that is not aligning to our horizontal vertical, system, and that's this applied force. So we need to find components for it. So we're just going to say, all right. Let's use pink for horizontal, and then we'll use green for vertical. All right, now we have the horizontal and vertical components. Now they kind of line up to our system that we need. Okay. Go back to black. Acceleration equals the net force of the system divided by the mass of the system. All right, well, we know that mg and normal force should kind of cancel out, right? But there's this other little vertical arrow over there, right? So now we have two upward forces and only one downward force, right? So all the upward forces have to cancel all the downward forces. This block is not going to magically float off the ground, right? That's not what's happening. So all the upward forces must equal the downward forces. So that means that normal force here, N, is going to equal mg minus this component, the green component of the applied force, right? Which is F, and this is theta here. So that's opposite, so it's sine, right? F sine theta, right? So if we took this component here, the green one, plus the normal force, we added them up, we would get mg, right? They have to all the upward forces must cancel all the downward forces. Okay, so now we have kind of derived that expression for n. N equals mg minus f sine theta. And now that we know what n is, we can do an expression for the force of friction. Force of friction equals mu times n, and n is this, so we're going to just kind of plug that into n over here. So force of friction will be mu times mg minus f sine theta. Right? So that's force of friction. Now we have this component. There's a little check mark there. We've done that one. We did this one. Mg is easy. It's just mg. And then we have this component of the applied force. Let's go ahead and write an expression for it. It's going to be f cosine theta because it's adjacent to the angle. Right? All right, now we have, without using any numbers, we have filled out our free body diagram. But even though there's no numbers, that's okay. So acceleration is, let's see, we know that all the upward forces aren't going to accelerate this object, right? All the upward and downward forces cancel. So all that's left over is the horizontal forces. So we have the positive force, F cosine theta, right? The pink one to the right, minus the friction force because it's to the left, So friction force, remember, was mu times mg minus F. I'm going to erase this little part right here because it's getting in my way. So 1 second. Just going to erase this. Okay. F sine theta. F sine theta. Okay. Divided by the mass of the system, which is just m. And that's really it. I could clean this up. You know, we could probably factor out something. We can factor out the F or something like that, but we don't really need to. Maybe let's go ahead and let's see if we can clean it up a little bit. But this works, right? This is an equation that would be satisfactory on like an FRQ, right? As long as you have it in the terms they want. Let's go ahead and clean it up a little bit. F cosine theta. Let's distribute the mu to both terms, right? Distribute that. So it'll be minus mu mg minus mu f sine theta over m. Let's see, we have really common, nothing to factor out, nothing to really cancel. I want to leave it like this. This process, you know, this looks messy, and it kind of is, but it gets the job done. So, all right, let's do we'll do a couple more problems. So let's go to the next slide. Let's see, let's do a pulley problem. I'm going to do 2 pulley problems with you. First, let's do one where simple one. So we have simple pulley. This is one just like on your worksheet. Let's do tomorrow. Let's say I have 2 masses on a pulley, little m and big M. So let's say little m is mass of 5 kilograms, and the big M has a mass of 8 kilograms. And I want to know what is the acceleration of the system, and then what is the tension in the rope. Now, there's 2 ways to solve this problem, and one is really long and annoying, and the other one's really simple and easy. Jordy, it's okay. Jordy doesn't like the long, hard way. Jordy, hey. So let's do the easy, quick way, because I like that better. The easy way is to think about this whole thing as the system. All right, Jordy, for real, calm down. If we think of the system as everything, the pulley, the masses, the rope, everything, it's all the system, everything that's circled, right? That's the system. The only forces that can affect the system, that can make it accelerate, are forces from outside the system, like gravity, or friction, if it existed, but this is an ideal pulley, so there's no friction. And that's really it, right, in this case. The tension is inside the system, right? It's within my circle I drew, so it can't do anything to the system. It's internal to it, right? So we're going to think about Newton's second law equals mass and acceleration. Now remember, this is the mass of the system. Jordy! Jesus. All right. What was I saying? Sorry, Jordy's going crazy. Remember that the mass of the system includes all the masses, right? So the mass of the system will be 13 kilograms. We're adding up, you know, the two individual masses. So all the forces here that are external to the system are just the weights, right? Remember, tension's internal. There's no friction. There's no normal force because we're not on a surface. We're hanging by a rope. So the only forces that are external here are weight. So we have, let's draw a Venn diagram for each weight. We have little m, right? And it's got its weight down, mg, and its tension up. We have big M, and his weight down, and his tension up, right? Now, these tension forces are the same, but again, they cancel out because they're both internal to the system. Real quick about direction. The direction that you assign, positive or negative, in these pulley problems is really important. You don't want to get confused. Do not assume that up is positive on both. It is not. Pick one side. Let's pick the left side first, okay, this side. Let's call up positive on this side. Follow the rope around. If you follow the rope, notice that what was up is now down, right? It's kind of followed over the pulley, and now it's pointing down. Well, that's still positive, right? So down on this side is positive, and up on the left side is positive. Let's call down negative on this side, and again, follow the rope. If it's down is negative here, kind of trace the arrow backwards, and that means up is negative on this side. Very important to keep your direction straight in these problems, because if you don't, you're totally screwed. Okay. Now we have a direction straight. Let's think about Newton's second law. So we have on the system, the forces acting on the system are the weight of the big mass, big mg, minus the weight of the little mg, right? And look at the signs here. Positive big mg, because we said down on the right side is positive, minus little mg, right? And because we said on the left side down is negative, right? So, and they must equal the mass of the system times the acceleration of the system, right? Which is what we're trying to find, because they're all connected by a rope. They're all the same. They all have the same acceleration. From here, it's really simple. Big mg is 80, because mass is 8, minus 50 equals the mass of the system, which is 13, times a. And we're going to solve for a. So 80 minus 50 is 30, equals 13 times a. I divide by 13, and I get a number 2.3. So it looks like our acceleration is positive 2.3 meters per second squared, which makes sense. We think it should go down on the side where the heavier mass is, right? So it should go in the positive direction. 2.3 seems reasonable. You know, there you go. Right? What about tension? All right, now when it comes to find tension, okay, you can't use this system anymore, right? Because this system, there's no way to find out what the tension force is, because the tension force is internal to it. You have to change what the system is. So now we're going to say the system is just one block. Let's use the big M. Okay, now the system is what's in pink. Now just that block is the system. Now the tension force is external to the system. So we can calculate it. What are all the forces on this new system? The pink system. Well, we have tension up, but remember up on this, for this side, up is negative, so it's negative tension, and then positive, it's weight, right? And we're over here in the pink system now. On this side, right? We're looking at just this system here. So down weight, which is positive, we decided that was positive, and up tension, which is negative. So let's put this out. So we have big mg minus tension force equals the mass of acceleration. But now we know what acceleration is, right? We know a, it's 2.3, and I know the mass, big M, was 8. So we have 8 times 2.3 on this side equals the weight of this thing, which was 80, right? Minus tension. So now we're going to solve for t. So 8 times 2.3 is 18.5, rounded up, equals 80 minus t here. Just separate this stuff. And then we're going to, like I said, solve for t. So we're going to subtract 18.5 from both sides. And that's 61.5. So the tension force will be 61.5 newtons. And there you go. That should be negative. Oh no, it won't be. Okay, that's fine. All right. The tension. You're going to get a positive number, or it doesn't really matter, because if you look at the rope, the tension force is negative for one side, but positive for the other side. So it tends to be like an absolute value. It's just a tension in the rope. Absolute value. So there you go. First, we use the system as a whole, one big system, to find the acceleration, and we broke into a smaller system, just one mass, to find the tension. All right. So look this one over for sure, because you're going to have several pulley problems tomorrow. All right. Okay, last one. We're going to do a tension problem. All right, where we have just hanging masses. So let's say we have mass like this, and a mass like this. And nothing crazy tomorrow. We're not going to have any problem on the test where there was like two angles from that one bonus problem I gave you, where you had two different angles. We won't have one like that tomorrow. At least not when we have to do math. There will be one like that, but we won't have math in it. Just conceptual. So let's say this mass is 100 kilograms, and it's hanging by these two ropes. And the question might be, okay, what is the tension in the rope? There's T1 and T2. Now, because the angle is the same, the tension will be the same in both. And recall, if we draw a free body diagram for this hanging block here, 1,000 newtons down is mg, tension and tension. And then the angle here was 30, and the angle there is 30. Okay, so how do we solve for the tension forces? Well, we got to remember that this object is at rest, right? So the total acceleration, the net force on it rather is 0. That means all the upward forces must cancel out all the downward forces. So that means this vector here plus this one must add up to 1,000. So if I know this side, and again, the same angle means they're both the same. Okay, so it makes it easy for us. This side must be 500 newtons, and this side must be 500 newtons. Right? Have to be. All right. Well, if we know one side of a right triangle and the angle, we can find hypotenuse, right? So we're just going to do our trig. Let's see. Let's use sine of our angle equals opposite over hypotenuse. I want to solve for hypotenuse. So that's the tension. Right? That's this part of the triangle here. Hypotenuse will equal, then I'm just going to rearrange the equation, equal the opposite side of the triangle divided by sine of the angle. So my tension force is equal to opposite side of the triangle, which is 500 newtons, divided by sine of theta, which is 0.5. So tension force is 1,000 newtons. Each rope is doing 1,000 newtons, right? So this one's doing 1,000. Sorry, this one's doing 1,000 newtons, and this one's doing 1,000 newtons. Even though the total weight is 1,000 newtons, right? Both ropes have to do 1,000 on their own because of the angle they're at, right? Imagine if it was one rope was straight up vertical like that, then its tension would be 1,000, right? But the bigger angle you get, right, the more obtuse you become, more horizontal, the more work the tension has to do. If this doesn't make sense, grab something. Grab your backpack, your purse, a book, and let it hang straight down from your side. And it's easier to hold on to, right? You don't feel much force there. Now put your arm off to the side like this and try to hold the same thing. And it's really hard, right? Because you're doing way more tension in your arm, way more force being applied than if it's hanging straight down. If you ever do these exercises where you have what is this called? The tricep thing? I don't know what it's called. But that thing, really hard, right? Now I can do like 120 pounds like this, but I also curl like 300. So, I'm like super strong, but you guys can wake up that much. But I can go over the what do you call it? The cheap seats, whatever. Anyway, you get the idea. Okay, I'll shut up now. All right, so that's 4 kinds of problems you got to know: elevators, tension, pulleys, and inclined planes. I hope that was helpful, and I'll see y'all tomorrow. And good luck studying, and